Okay, let's see where this quantization of angular momentum gets us. If we look at this relationship between the angular momentum mvr and the quantization relationship mvr is equal to nh bar, n is an integer, we see that this provides us a relationship between the velocity and orbital radius of the electron and an integer. Okay, and so what this says is that we know that the velocity and the orbital radius both are related to the energy of the electron, because the velocity, 1/2 mv squared is its kinetic energy, and the potential energy is related also to its distance from the nucleus, r. And so what we can already guess just from this quantization of angular momentum is that this is going to lead to a quantization in the energy of the electron. That is, the electron energy is now going to take on only certain discrete allowed values, and thus we call that quantization, the quantization of the energy. So let's see how this goes. So we start with, again, the quantization of angular momentum. So we have L is equal to mvr is equal to nh bar. Okay, and if we rearrange this and solve it for v and square it, then we get that v squared is equal to nh bar over mr squared. Now, don't get confused here. N is an integer, m is the mass. Okay, these are not both integers. M is the mass. It's the mass of the electron. If I should probably put a little subscript e on all the m's to remind you that it's the mass of an electron, but that's too much writing, so I'm not going to do it. Okay, so what this gives us then is now we have a v squared, and so the kinetic energy is equal to 1/2 mv squared, again, for a non-relativistic particle. And so this is equal to 1/2 m times nh bar, that's an n, h bar over mr squared, which in the end we already saw that this is also equal to 1/8 pi epsilon naught times ze squared over r. Okay, so now we have a relationship between r, which appears on both sides of the equation, and n, the quantization number, basically the principal quantum number. N is what we call the principal quantum number, but it's just an integer. Okay, and so let me actually write that. So n is the principal quantum number, and this is going to disappear when I go to the next slide, but now you have it in the at least in the lecture video. All right, so now if we solve this equation for r, then we'll see that the r's are now quantized. Okay, that is, the orbital radii can only take on certain discrete values. Okay, and so let's so we have, let's just make a notation here. We have the allowed orbital radii. Okay, and these are we'll put a subscript n on these radii just to remind us that it's quantized by the principal quantum number n. So I'm just solving this this equation, the equation above here for r, and then I'm going to write this term separately over z. Okay, and it turns out that this quantity here, we typically this is a group of constants, right? The mass of an electron, the charge of an electron, h bar epsilon naught 4 pi. So this is just a constant, and we call that a naught, or the Bohr radius. And so what we have is that the allowed orbital radii are equal to the Bohr radius times n squared over z. So again, this is the Bohr radius.